Hello, good afternoon. My name is Elaine. I am a biologist on the Glasensor team, and I have here with me Rebecca, who is a biomedical engineer, and I have two of the electrical engineers here, that is Zemo and Chris. And today I'm just going to talk you through the innovation of our biosensor. So Glasensor is a team of 8 students through 3 different disciplines, and we've all taken the SensUs objective of developing an innovative biosensor very seriously in all aspects of our biosensor. So our biosensor is based on using one single technology to both give us molecular recognition and also flow actuation mechanism, and that single technology that we use is heat. So when we were first thinking about what we wanted to do for the molecular recognition, we were having issues with trying to get over the fact that adalimumab is so similar to human IgG1, we weren't going to be able to distinguish it. So we were thinking about this for a while and then decided to actually think outside the box and use this similarity to our advantage. And we combine this with all the information that we already know about therapeutic antibody stability under certain different stresses. And one of these stresses is heat. So we use these characteristics to base our biosensor and our molecular recognition system. So on step 1, what we do is we capture adalimumab by using a capture antibody. Step 2, we put it under heat stresses of high temperatures at 80 degrees Celsius. And at step 3, we expect adalimumab to begin to unfold, but then aggregate at these high temperatures. And at step 4, we then use a fluorescent tag. It's a tag for thiol groups, and then we can quantify this change in thiol group numbers as adalimumab aggregates. I'll then pass on to Rebecca.
For the flow, we also had to use heat. This meant we had to custom make a cartridge because we have 2 different flows at 2 different times and 2 different speeds. For this as well, it had to be disposable. The whole cartridge was disposable. So for the waste, we made recessed waste chambers to stop the waste flowing back into the system, keeping it disposable and making sure that we didn't have to use pumps within our device. For the 2 different flows, we had to custom build a heating system as well. So for the electrical team, this was quite a challenge because the entire heating system has to fit within our biosensor, has to all work together, and has to make sure the 2 different speeds are correct. For the heating system as well, there is a stage within it as well because the contact has to be exact for the exact temperatures that the biological system needs. We also custom built a sensing system because we needed correct heights and things for the correct sensing of the tag. The machine looks like this. We've got the things here and all this. It looks quite nice, but it is also quite compact, which is down to the electrical system. Have you got anything else?
No. Well, I'll basically summarize. So basically Glasensor, the biosensor that we developed, the idea of actually developing everything by hand, our kind of main focus is having a homemade biosensor. Everything is homemade because it allowed us to have our own specifications. It's a customization basically, and we take a lot of pride in that, and we think that that was really useful in creating innovation in our biosensor. But yeah, we can answer any questions if you like.
Thank you very much. Interesting concept. It's absolutely out of the box, I would say. I had a question about this process with the heating and the cooling, because you talk about the aggregation and of adalimumab. That must be quite, let me rephrase it. Can you comment on the reproducibility of that? Because if there is a variability in the amount of tile groups that become free for reaction after the aggregation and the changes in structure, then you inherently get variation in the signal that you get if you repeat it, for example, 10 times. Can you say something about that?
Yes, I think I understand your question. So yes, you are correct. So from what we know, that antibody stability, this aggregation, there's a lot that can affect it, pH, buffer, so on and so forth. So if we are, in theory, if we're able to stabilize, if we're able to control that and standardize that, we would use a standard buffer, standard pH, standard environment, then the aggregation that you should see should be dependent on, obviously, their adalimab concentration. So the higher their concentration, the more aggregation you perhaps see. But then maybe there's more thiols as well in relation to, obviously, a smaller sample. From the calibration curves, with the curves that we've looked at for correlation, they do seem to fit.
Okay.
I don't know if that quite answers your question. Unfortunately, I'm a biologist. I'm not quite a biochemist. I've tried to learn as much as I can, but from what I understand in acid development, our correlation graphs work out and they are reproducible.
So that means that your calibration curves, they are linear in the range from, let's say, 1 to 10, or?
Yes, we got proof of concept that today.
Clear.
Actually, I would like to follow up on that concentration. So in your team result document, you were at very high concentration. So you were able to achieve to bring it down to?
Yeah, that's why I was emphasizing today. We were able to bring that down.
No, so what have you done to bring it down? So what's different now?
Yeah. So yeah, you're correct. When we first did this, we were limited because of the timing. We were working along, because it's a multidisciplinary project, it's a chicken or the egg situation. We couldn't get the biosensor made without the other teams from having specifications from us. So that's how we ended up having such a high concentration. We looked at such high concentrations for proof of concept, for that correlation, because of technical issues in the lab, basically. And so we were happy to keep going forward with this project and not changing our concept, because knew we were always going to use microfluidics. And the amazing thing about microfluidics is it can really change your specificity, basically. So, decreasing these concentrations, we were still convinced that we could see this correlation as low a concentration from 0.5 to 10 micrograms per mil, which we did.
Right, thank you. I was just going to ask about the results as well. But then I can ask about your sample preparation and the pre-sample preparation and storage and all that kind of stuff. Have you considered that?
Yeah. So you want me to just describe it? Okay, no worries. Sorry. So our sample in the competition today, we don't have a dilution factor at all. We took a 15 microliter sample, which I believe is well within the competition ranges. And literally it just requires a aliquot of sample onto our chip, insertion of the chip, and everything else is automated. That is the ultimate goal.
Okay, thank you.
So does that mean that you do store the other chemicals also on the in the disposable?
Yeah, it is really cool, but I'll let Rebecca talk about it.
Okay, so this was a problem I had where we had tried to plug the channels to keep everything separate. We used wax, it didn't quite work. So I went down a more mechanical route. There is a hat that sits on top and it's got spaces so you can turn it so the channels are open or closed. So we fill everything like this. So everything is filled, the hat is put on, and then we can open channels or close them.
So all reagents are within the cartridge and they're stored within the cartridge. The idea is the cartridge will contain all wash buffers, all of the thiol tags and the antibody as well in the reaction site, and then that itself is stored perhaps in the fridge, cooled. But yeah, there's no other reagents.
And do you have ideas how that can be produced later on if you have to make multiple disposables?
So my idea was you keep the hat on the cartridge, it is delivered as that, and we've actually made little handles you pop onto the cartridge, and later on it will become motorized. So you just put the cartridge in, the handle attaches, and it just turns when it knows when to, after the wash, after the tag.
But we have discussed about mass manufacturing, possibly other methods that we could use for that, because obviously it's quite small fluids, small volumes, that you're adding to a cartridge.
Okay, very nice. In your report, you also mentioned the PCR film, which is placed on top of the sample, I think. Can you maybe comment on that, or what?
So underneath each cartridge is PCR film, and then on top of that we have a small piece of glass which has the antibodies on it. So that was made by the biological team, and then above that there is another PCR film, but that is not as heat resistant. It doesn't have to be, but the whole cartridge had to be very heat resistant, obviously for such high temperatures. But the glass increases the heat transfer through to the antibodies in the sample, so it will always have to have a film on it when we produce them.
The film on top is to prevent your sample simply evaporating. That's what allows the flow mechanism.
Okay, so in at all these locations you use it as a temperature conductor.
Yeah, yeah.
Okay, okay.
It's a very nice idea. Definitely an out-of-the-box idea. The reaction between a bromoalkyl moiety and a thiol moiety is known to be a fairly slow reaction, slow kinetics. Is there a possibility that incubation for slightly longer times with the between the dye onto the sort of protein omelette that you create on the surface could result in strong errors, like in strong differences in fluorescent, like even differences of a few seconds or, say half a minute in incubation for, careless of the operator, could result in a lot of error in terms of fluorescence of the surface.
So the fluorescent tag was quite difficult. We weren't sure what to select. There's quite a lot out there, which is why we were quite keen to tag thiols, because there's so many fluorescent antibodies out there already. We ended up selecting this one because out of all the antibodies we could find, it actually had the lower incubation period. I understand there are antibodies out there that you could quench, so I think it's, if I understand your question correctly, it's to stop your seeing your variability. So MBBR, unfortunately, I don't think works that way. The idea was that we could, at the moment, improvise and read, if we standardize when we read, basically from when the sample, MBBR gets added to the sample, and then from when we read, that standardization would, help decrease the error. But it's definitely something we would look at. This project was quite challenging. I don't know why we made it so hard for ourselves. There are a lot of aspects that we need to look over, from things like materials. We need a lot better heat-resistant materials. We just used what we had at the time, and even the reagents as well. That was quite difficult to select. We didn't have a lot of time to play around with different types of reagents, but that's something we will be looking forward to do in the future.
Have you seen if variabilities in concentration of thiol displaying proteins in the plasma, like albumin, which has a free thiol, a free cysteine, and can vary among patients? If you have a non-specific absorption of albumin onto your surface, could that cause troubles? Have you guys thought about it, factored it in?
Yeah, because we're working with antibodies, it's always tricky. Proteins, antibodies, they're all very tricky. And we have only recently been able to start testing on plasma. And obviously you've got so many interfering molecules in there. So we've not had time to explore it, but we will look into it, and we do expect issues that we'll need to deal out.